Good evening, everybody. It's 6 o'clock, so we're going to go ahead and get started. And just a reminder, I've already shared in our Zoom chat and in our YouTube and Facebook online chat, you guys have access to tonight's webinar notes. So if you need them now for tonight, and you can work them out as we're actively going through it, or if you just want them for later to go back and review, check out the chat. You have access to those notes. So guys, welcome to our chemistry webinar all-in-one. I'm going to go ahead and just talk about a few things about Archer Review quick while a few more people are hopping on. All right, so when we take a look at this graphic here, you guys have multiple QR codes that you can access to see everything that we have to offer you at Archer Review. Obviously, we've got our free live webinars. Tonight's is chemistry, but you can check out more science webinars like anatomy, physiology, biology, scientific reasoning, or you can check out live webinars for math, reading, and English as well. So you access that QR code and you can see any other upcoming live webinars that are available. You can also re-watch webinars that maybe you missed or just want to go back and freshen up your knowledge on. So we've kept a library of all of our webinars. They're all recorded, so scan that QR code if you want to go back and re-watch some others. At Archer Review, we've been working really hard for you guys on our current question bank. So we have revamped our question bank for TEAS, and we are still adding to it to make it even stronger and more aligned for all of you so that you see even greater success passing your TEAS exam. So please scan that QR code to access our free question bank. And I should mention that it's free for a trial period, not indefinitely, but it gives you a really good taste of what we have for you. We've got on-demand videos to support you in your learning, to help you with your TEAS exam. These on-demand videos go into each topic that we're going to cover tonight, but in much greater detail. Tonight, if you've ever attended a webinar, you know it's fast, it's a crash course, it's speedy. It's very surface level. So maybe throughout your time tonight, put a little red flag, make a spot in your notes, notice the areas that you do really great in, and notice some of the areas that you need more practice or, that pace slowed down, or just some other ways of explaining these concepts. That is where you would really benefit from using our on-demand videos. So if you find yourself in that situation, scan that QR code to check out way more that we have to offer at Archer Review. We also have fabulous tutors. All of our tutors are currently either in education or have been educators in the public school setting or community college level. We've got Brandon with math, we've got Tammy with English and reading, and we've got Shelley with science. And they are available for you all to support you either one-on-one or in small groups. So take advantage of those tutoring opportunities. And then recently at Archer Review, we have included a couple of packages for you guys. So the first, I'm going to go ahead and actually switch my screen. It breaks down the SurePass and the SurePass Pro packages into some greater detail here. But you have these QR codes in your notes, and I'll pop them back up at the end as well for you. But these packages, the SurePass and SurePass Pro, include multiple things in these packages. So let's talk first the SurePass. That's that top section you're looking at here. Our SurePass option gives you access, full access, so not a free trial period, but a full access to our question bank and our on-demand videos. You get access to both beyond the free trial period, okay? But then, if you want to level up and really take advantage of an extra perk, you can take a look at the SurePass Pro option. So that's the bottom part of this visual. You will get the question bank, You will get the on-demand videos just like in the SurePass package, but what you're getting here in the Pro option is access to a tutor. So you will have a full hour to use with a tutor. That can be in your math, that can be in science, English, or reading, whatever area you feel like you would benefit the most in. If you were to purchase the SurePass and then maybe say you needed a tutor later on, you'd end up paying a little bit more. So if you just bundle it all together with that SurePass Pro option right away, you would save money in the long run. All right, next up then is the TEAS webinar feedback survey. I'm just showing this to you early tonight so that you can scan it, and just so we don't forget, at the end of this webinar, I am a passionate educator in public schools. During the day, I teach high school science courses, and I just really value feedback from my students. I want to make sure your guys' time tonight is of value. I want to make sure that it aligns with what you need from us at Archer Review to help you with your TEAS entrance exams. So please don't forget to complete this survey at the end of this webinar tonight to, let us know the things that we are doing well, but certainly give us that constructive feedback too. How can we better serve you guys? So don't forget about that survey. But let's go ahead now. I think that was plenty of time to let everyone get logged on. So again, welcome. Tonight's webinar is about chemistry. And I always like to give a plug to my students about chemistry because a lot of my students are, pre-nursing students or some sort of medical field student. They're like, well, I love, the human body and biology. Like, oh, chemistry sometimes, just it's challenging, or what's the connection? And so I always try to remind students that, guys, without chemistry, life does not exist. And so if we want to better understand the workings of living things, but especially the human body and our patients, we need to better understand what is going on at that molecular level, causing things like cells and tissues and organs to be properly or not properly functioning. So that's the purpose of our chemistry webinar tonight. Let's go ahead and get started with the basics with atomic structure. Okay, so atomic structure means atoms. What are atoms? Atoms are the smallest building blocks of all matter. So not just life, but everything in existence is made up of atoms. Atoms cannot be broken down any further. It's that simplest unit, that simplest building block. For us to continue breaking down the structure and function of atoms, we definitely need to review how scientists represent all the useful information about all types of atoms. So specific types of atoms are called elements, and they're arranged on the periodic table using element symbols in their own little square. So in each square, you will see a symbol, you will see the atomic number, and you will see the atomic mass. Now, all periodic tables kind of differ in regards to, is that atomic number on the top or is the atomic number on the bottom versus the atomic mass. So a nice little trick to help you remember this is that atomic number will always be a whole number, so as opposed to the number down here with the decimal, and it will always be the smaller number of the two. Okay, so just to help you remember that in case you come across a periodic table where they're flipped. So let's talk about all components inside of this element box. So first and foremost, you've got this symbol. So for our example here, we're going to look at the element Si, okay, and that is going to represent silicone, a different wording here from this periodic table. So the element is going to be silicone. When you look at that whole number there at the top, it is 14. What in the world does 14 refer to? It's the atomic number, and the atomic number is going to mean the number of protons. So in silicone, there are 14 protons. We'll talk more about what those are in just a minute. But also don't forget, if silicone's in a neutral state, the atomic number will also tell you that there are 14 electrons. And we mean neutral because the number of electrons will cancel out the number of protons. So when number of protons, 14, equals the number of electrons, 14. They cancel each other out. It's a neutral atom. But that doesn't always mean that atoms are always found in that neutral state. We'll talk more about that later. But just to always remind you that atomic number will for sure tell you number of protons, but then when it's in a neutral state, it'll also tell you the number of electrons for this element, silicone. The atomic mass then, what's this other number with these decimals? Why is it different? Well, the atomic mass will include the number of protons and the number of neutrons. And again, more coming on that in the next couple of slides, but there's just a simple breakdown. So let's talk about each one of those in greater detail. Looking at the structure of an atom, you see at the centermost portion of an atom is what we call the nucleus. And there's two different colored things inside of this nucleus. And then looking around the nucleus, we've got these rings or orbitals. Now, these rings or orbitals aren't a true structure per se. It's just a model that we draw out to give a visual to space around that atom or around the nucleus of the atom. So let's talk about the parts then that are found in each one of those areas. An atom can be broken down into 3 subatomic particles, all of these that we've already mentioned when we looked at the periodic table in the previous slide. So found inside the nucleus here is 1 subatomic particle, the protons. And we've got the protons labeled here with positive picture, that positive sign, because protons have a positive charge. Protons have a positive charge. Another subatomic particle found also in the nucleus are neutrons. Notice neutrons don't have a sign on that blue circle for neutrons because neutrons are neutral. They don't have a charge. They are neutral. Protons and neutrons both have 1 atomic mass unit. This is why we factor protons and neutrons into the atomic mass value that we find on the periodic table. There's enough of a weight there to quantify it. When it comes to electrons, they have a 0 atomic mass unit. Well, all matter has a mass, otherwise it wouldn't exist. Electrons just have such a small mass that when we want to round it up, it's essentially 0. So electrons are not factored into that atomic mass value that we use on the periodic table. But electrons do have a charge. Electrons have a charge of -1, and you can see these electrons with that negative picture on these circles, and they are found around the nucleus. Electrons orbit the nucleus, and that's why we call these areas orbitals or shells, because this is just representing the space that electrons exist in. All right, so with protons, don't forget, they're located inside of the nucleus. We represent them here on these pictures with the red circles with the plus signs in the middle. Those are the protons for each one of these atoms: helium, carbon, and neon. A proton determines the atom's identity. This is really important to remember, you guys, when you're looking at a periodic table. So I'm going to actually go back a couple of slides. So see how silicone's atomic number of protons, says 14. 14 then will always represent silicone, no matter what. But when you move on to the atomic number 15, we're saying that this atom has 15 protons. You are now talking about a completely different atom, and in this case, it would be phosphorus. So the number of protons determines the atom's identity. And don't forget, protons contribute to the atomic mass. All right, a quick recap about neutrons. Neutrons are also found in that nucleus. Remember, we're using the blue circles here for the neutrons. They are not showing a charge, positive or negative, because neutrons are neutral. But they do have one atomic mass unit, so neutrons do contribute to the atomic mass. A quick way, using math, to help you find the number of neutrons, especially when only looking at a periodic table. If you don't have a visual like this to sit here and count, oh, helium has 1 and 2 neutrons. When you're only using the periodic table, how can you use those clues on that element's box and symbol to find the number of neutrons? Well, you take the atomic mass, that bigger number, and you subtract out the atomic number, the smaller whole number. That will leave you with a difference, and that difference tells you how many neutrons that there are inside of the nucleus of that atom. So again, let's practice looking at helium. If we're looking at helium's nucleus, we see an atomic mass. There's 4 pieces inside of this nucleus here, 2 reds, 2 blues. We know the helium's atomic number is 2, meaning that there are 2 protons. So take 4 particles, subtract out the 2 protons, and what do you have left? You have 2 neutrons. So that's how you take atomic mass minus atomic number to figure out the number of neutrons. This is especially helpful when you only are working with a periodic table and you don't have an atom all laid out for you. Now, elements exist, though, in like alternative versions of themselves simply because those number of neutrons we just talked about can change. They can vary. So these are called isotopes. Isotopes are atoms that have the same number of protons, but a different number of neutrons. Therefore, you can see a difference in these atoms because their atomic mass will be different. Let's work that out looking at oxygen isotopes. I've got 3 oxygen isotopes before you here. This first one is oxygen 16, we'll refer to, and you've got your atomic number and we've got the atomic mass. So remember, protons, the number of protons, the atomic number, will always identify your atom. That doesn't change. See how there are always 8? Because 8 is always going to tell us we're working with an oxygen atom. So 8 doesn't change. The atomic number of protons is consistent. But what you do see change is this bottom number, that atomic mass. Well, knowing atomic mass is made up of protons and neutrons, and we just said protons don't change, then that means we're changing the number of neutrons, which is exactly what an isotope is. So for this first oxygen 16, if there are 8 protons, subtract 8 from 16, and then you are left with 8, right? You're left with those 8 neutrons. Moving on to the next oxygen atom, there are still 8 protons, but now you have 17 for that atomic mass. It gained mass. So how many neutrons are here? Take 17 minus 8 and you end up with 9 neutrons. Furthermore, oxygen 18, follow that same pattern. The mass has gone up, but the number of protons has remained the same, so that must mean it's taking on another neutron, and it did. 18 minus 8 is 10. So why are they gaining neutrons? How is this helpful? Well, isotopes are helpful really for many reasons. We use them in science to date fossils, for example, based on like the rate of reactivity and how long it takes for these isotopes to break down. There's a rate at which we can measure, and then we can equate that to a time period. But isotopes, specifically in the medical world, are really helpful with diagnosing and treating like cancer or heart conditions, and we even use them for bone scans. So understanding isotopes is useful for medical technology, especially in the medical field. Okay, let's practice using this element, the symbol, atomic number, atomic mass, and let's just break down some basic pieces. So for this carbon isotope, carbon 13, what is the atomic number? How many protons does carbon have? What is the atomic mass? And how many neutrons are there? I'm going to give you a few minutes to work these questions out, and we'll talk about them as a group. Thank you to those who are sharing their responses in the chat. This is a great time for me to remind you all, or let you know in case you haven't joined a webinar before, that in our Zoom chat room, we've got it set up so that you guys are able to share your responses, and only I am able to see your responses. So if that makes you feel more safe or confident in sharing what you think, then please go right ahead and continue to share in that Zoom chat. Again, only I can see them. And I like to see them. I like to see how you guys are doing along the way. If you are sharing your responses on YouTube or Facebook, I am not able to adjust the privacy settings for you there. So what you are sharing, others are able to see. But you know what? That's okay too. If everyone's here to learn and learn from each other, hopefully you feel like it's a safe space to go ahead and share what you think, right or wrong. We're all here to learn. So just giving you a heads up there. Let's go ahead and go over these practice questions for carbon 13 isotope. So the first one is, what is the atomic number? That atomic number, remember, is going to be the smaller number of the two, and typically on a periodic table found towards the top. So the atomic number is 6. Let me click my next button here. There we go. Now you can see the answers with me. Atomic number is 6. How many protons does carbon have then for this isotope? Well, it's the atomic number, so it's the same answer here. The atomic number is 6. That means you got 6 protons. And remember, that's what's telling you you're working with a carbon atom. What is the atomic mass? That's the bigger number, typically found towards the bottom of that symbol. So the atomic mass is 13. If the atomic mass is 13 and you have 6 protons, how many neutrons do you have then? So take 13 minus 6 and you are left with 7 neutrons. But let's move on and talk about the last subatomic particle, which are electrons. Remember, electrons we're noting with these green circles, and they've got this negative charge inside. So electrons, these green circles here, they orbit the nucleus. They are not found in the nucleus with protons and neutrons. Electrons are found outside of the nucleus, and we call that space the orbitals or the shells. You'll hear those words interchangeably. But electrons have a negative charge. So these shells, how many shells, you see that they kind of differ from one atom to the next, and they even differ, look at neon, they differ in how many electrons can be found in each orbital. So a trend to just remember is that the atoms that the atoms with that first shell will always have 2 electrons in that innermost shell. That is the most amount of electrons, because of their energy, that that shell can hold. So that very first shell for any atom, doesn't matter, helium, carbon, neon, look at them all, they can only hold 2. But for every shell after that, if there are more electrons remaining, like in carbon, carbon has more than 2. Helium only had 2. Carbon has more. So where do these others go? In the orbitals around that first one. So any shell or orbital beyond the first shell or orbital can hold 8 electrons. So just first 2, then 8. But these electrons help you to understand and helps you to predict or determine the chemical properties of each atom. So let's talk more specifically about that through the lens of valence electrons. Valence electrons are the outermost electrons. So we're not talking about all electrons, especially not the ones in that innermost shell if you're looking at neon. But we're looking at the outermost shell. Those electrons found in that space, these are known as valence electrons. And these valence electrons actively participate with other valence electrons. And that's what creates our chemical reactions. So these valence electrons can either be, transferred from one atom to another. One atom completely gives these valence electrons away. Another atom is happy to completely take them. Other atoms, they don't really take or gain or lose. Instead, they share. So we'll talk more about that, but I just want to give you that idea. Valence electrons, those outermost electrons, are the active participants that create and give rise to chemical reactions. And there's patterns on the periodic table that help us understand this and make those predictions. And I'll give you more on that in just a moment. But for the atoms that take on, I'll go back to this slide here. Atoms that take on electrons or atoms that lose electrons, those have specific names. We call those atoms ions, simply because they take on a charge. So if an atom is willing to lose electrons, we know electrons have a negative charge to them. So if it gets rid of something negative off of itself, it overall becomes more positive. So that we would call a cation. A cation is a positively charged ion. It's an atom that gave away its valence electrons. So now the ratio of protons to electrons is unbalanced, and it's in favor of the protons. There's more protons than electrons, and protons have that positive charge, and there's fewer electrons in this case. So overall, this atom is more positively charged. And a fun way to help me remember this, or actually, there's a couple ways. I've always been an animal person, but especially I love cats. So cats to me are positive, and so I do a couple play on words here for you guys. Sorry if you are not someone who enjoys cats as much as I do, but hopefully it still helps you remember nonetheless that cats, you can come to the good side, guys. Cats are positive. They're wonderful. And so we see cation with that positive play on word there. But, again, you're not a cat person, take a look at this. This will help you out too. Take cation, and instead of using that letter T, insert like a positive sign to give you that T look. And that will help you remember a cation has an overall positive charge. Some examples here, look at all of these elements, and they all have that positive charge next to it. And then on the flip side, then we have atoms that take on extra electrons. They want those electrons. Well, if they take on more electrons than they have protons, remember we're getting out of that neutral state, then that element becomes overall negative. And since there's a negative charge associated with it, it's still an ion and it's a negatively charged ion. So remember, they have more electrons than protons. And here's some examples here, and they're all annotated with that negative charge symbol, giving you an idea that they have a greater amount of electrons than they do protons. Let's take a moment to check in and practice. On the TEAS, guys, when you break down how many science questions there are, and how much time you have to answer your science questions, you're down to about 1 minute per question. So I'm going to try to stick with that as we do our practice questions tonight. I will mute, give you some time, about 1 minute per question, and then we'll check back in after a minute is up. So here's your question. A chlorine atom has 17 protons, 17 neutrons, and 18 electrons, and an atomic mass of 34. What is chlorine's charge, and would it be considered a cation, an anion, or neutral? Go ahead and give yourself 1 minute to work this out. I'm seeing some great responses so far from everybody sharing what they think. So let's go ahead and talk it through. For this chlorine atom, if there are 17 protons compared to 18 electrons, okay, so right away we have a discrepancy. We don't have equal number of charges. So there is one more electron, 18, than there are 17 protons. And electrons have an overall negative charge. So that means this chlorine is overall going to have a -1 charge. And since it's a negative charge, it would be considered an anion. So good job to everybody who participated in answering that. One more trend that I want to bring to your attention, because it will be really helpful for us later when we get into chemical reactions and equations, is understanding more about how to interpret the periodic table beyond just the individual elements and what's inside each box. But the periodic table is truly a very highly organized table model. It's organized from left to right, top to bottom, and in more than one way, I should say. So for example, when looking from left to right, we would be increasing in size, but notice how we are also seeing groups or families, these vertical columns, how they're color coded here, like red, orange, yellow, blue, purples. So these vertical columns, known as groups, or sometimes families, will share the same number of valence electrons. Remember, valence electrons are the outermost electrons around that atom. So for hydrogen, lithium, sodium, potassium, they're all in that same vertical column, so they will all have the same number of valence electrons, which helps you make a prediction how reactive is this type of atom, and in what way is it going to, get rid of valence electrons? Is it going to take on more valence electrons, or is it going to do neither? Is it going to share? So we can use these trends in the periodic table to help us make those predictions. But then going down, so not looking at columns, but looking at rows instead, these are called periods. So again, periods are these horizontal rows. And the number of row that an atom is in tells you the number of orbitals around that nucleus. What a cool trick that is. So for helium or hydrogen and helium, they're the two in that very first period. They only have one orbital around them. And remember, we said that first orbital can only hold 2 electrons. So you can begin to just even look at a model like the periodic table and use those patterns to visualize an atom. The periodic table is really an essential tool that you should really invest in trying to understand those patterns to help you make those predictions and determinations about each type of atom. So let's recap section 3.1, which is all about the atomic structure. Atoms, remember, make up all matter, not just living matter, but all matter. Atoms are made up of subatomic particles like protons, neutrons, and electrons. The atomic number will tell us how many protons are in that atom. You can use the atomic mass to figure out how many protons and neutrons there are in that nucleus. And isotopes are always going to be the same type of atom. Like, you're never changing that oxygen, remember? It's always oxygen or it's always carbon, but you are playing around with the number of neutrons for that atom, which changes that atomic mass. Atoms that take on electrons, give away electrons, those are going to be called ions because they have a charge if you're playing around with that proton to electron ratio. Valence electrons are the electrons in that outermost shell for an atom, and it is essential when it comes to understanding chemical reactions. And remember that periodic table is an essential tool organized by periods and groups to help you make predictions about chemical reactivity for each atom. I should probably try to pick up the pace a little bit here since we've got multiple topics left. So let's go ahead and move into physical properties and changes of matter. So just a reminder, what is matter? If atoms make up all matter, matter is everything that exists in your physical and natural world around you, and it's made up of those atoms. But all matter has physical properties to it that's measurable. And those properties are mass, volume, and density. So mass measures the amount of matter that makes up an object or substance. Volume measures the amount of space an object or something or of substance takes up. So with mass, we've got how much stuff, how many particles, and then volume is, given that amount, what's the amount of space that those particles take up? And then density is just the ratio of the two. Density, you take the mass divided by the volume. And again, it gives you a ratio. But matter can exist in various states: solids, liquids, and gases. Solids are solid simply because the particles of that matter are tightly packed together. They're tightly packed, they vibrate in place, but they hardly move around. And because of that, they take on a definite shape and a definite volume. Liquids, these particles move around more freely. Okay, so they're not tightly packed and dense. They're not vibrating in place. With a liquid, they're moving. They're not packed into place. They're moving freely. And because they move, there is no true definite shape. A liquid will just take on the volume, the shape of whatever container it is in, because it is able to move. It's fluid. And that means that there is no definite volume. Gases, you amp up the energy even more here. So gas particles move, I should put the most free here. They have the most energy. And because of that, gases have no true shape and no true volume. Given the states of matter, though, matter can change from one state to another. We call those phase changes. So looking at this model here, you've got arrows going every which way. We'll break them down. But you can see solids can become liquid, which become gas, and then gases can become liquid, which can become solid. They can reverse. Solids can jump all the way and become liquids, or excuse me, gases, and skip that liquid state. Well, and the opposite is true. Gases can completely become solids and skip that liquid state. So let's talk about each one. So this pattern here, looking at solids becoming liquids, which can become gases, this pattern shows how phases of matter change when heat is added or when heat is gained. Notice how if you start in solids and move into liquids, these particles like loosen up, they move. Remember how we talked about liquids? Those particles move more freely as opposed to solids, which are densely packed. As you add heat, that excites the particles, which allows them to have more energy to move. So really, when you're looking at the phase changes, you're just interpreting how much energy or heat is added or taken away as you move from one state to another. So when solids become a liquid, we call that melting. When liquids become a gas, we call that evaporation. Let's go the opposite direction. This pattern shows how phases of matter change when heat is lost. So if we start in that gas state and we remove heat, which is energy, those particles tighten or become a little bit more condensed than the previous state. So when we take gases and we go to liquid, we call that condensation. Condensation. And then when liquids become solids, we take away even more heat. And what do you notice? These particles aren't moving around anymore. Instead, they become the most dense and tightly packed together. And we call liquid to solid freezing. Freezing. All right, but two phase changes that I, often hear from students they don't see or experience as much are, one extreme becoming another. So if we have solids that become gases, so it just completely skips that liquid phase altogether, we call this sublimation. Solid becoming a gas, sublimation. And if you've ever worked with dry ice before, you've seen sublimation. So dry ice, think of a chunk of ice, and as it's exposed to the elements, it just evaporates. That's sublimation. But then the opposite, taking gas and condensing it, taking all that heat away and turning it back into a solid, is called deposition. So a gas skipping the liquid phase and going right into a solid. So think of frost forming on a really cold surface just from water vapor in the air. If you live in an area that experiences really cold temperatures like that, I'm sure you've seen that. That is called deposition. Okay, let's check in on your learning so far. So our practice question says, a nurse helps to remove a tumor from a patient's body and sends that tumor off to the lab. The lab analyzes the tumor and collects data on it in order to know how much space that tumor occupied in the patient's body. What property of matter are you analyzing here? Is it mass, volume, density, or length? So I'll give you 1 minute to think this one through. Good luck. That minute sure does go by quick, you guys. So, if a nurse removes a tumor from the patient's body, sends the tumor off to understand how much space that tumor occupied in the patient's body, that is going to be analyzing volume of that tumor. Okay, so volume. Mass, remember, is just how much of that substance, but it's not accounting for the space that it takes up. Volume is not only the amount of stuff in that tumor, the mass, but also how much space it takes up. Density is going to be the ratio of mass to volume, which she's, as, or I say she, I should not put a gender there, I just put a nurse. But any nurse who is sending in this data is not looking for the density, how compact are these particles in that given amount of space. They just want to know how much space in total it's taking up. And length we can rule out because length is only going to measure the amount of space in one direction, not in 3D. All right, our next question. Which state of matter is characterized by having neither a definite shape nor a definite volume? These particles are widely spaced and move freely at high speeds. Is that a solid, a liquid, gas, or plasma? You've got 1 minute. For those that chose gas for your state of matter, you guys are correct. So let's talk about why the others aren't correct then. Solids are going to have a definite shape and a definite volume. And solids, those particles are tightly packed together. They're not widely spaced and they just vibrate in place. They don't really move freely. So solid in every which way, you can rule out. Liquids don't have that true volume. They take on the shape of whatever container that they're in. Those particles are somewhat spaced apart, but they're not really moving completely at high speeds. So liquids, it's a little closer, but definitely doesn't fit all criteria here for this question. And then gases, all of these criteria fit gases. Remember, they have the most energy of the three. But we didn't talk about plasma, so let me mention plasma. Plasma does share some characteristics with gases, like having no definite shape or volume, and they do have particles that move freely. But here's the difference. Plasmas has these like unique electrical properties, and the presence of those charged particles really set plasma apart from gas. We never talked about plasma. I don't reference anything about charged particles given these circumstances, so hopefully you were able to rule out plasma pretty quickly considering we never talked about it. Let's do one more practice question. Actually, maybe I've got a couple here. Yeah, we'll go ahead and do this one. So in healthcare settings, understanding the behavior of substances during phase changes is important. Which of the following best describes this phase change that is occurring? When you have an alcohol-based hand sanitizer and it evaporates from a patient's skin, is that going to be considered freezing, condensation, vaporization, or sublimation? Give yourself 1 minute. All right, when an alcohol-based hand sanitizer evaporates from a patient's skin, that is considered vaporization. Hopefully the term evaporate sounded a whole lot like the word vaporization. But let's talk about why this is correct and why the others aren't. So option A for freezing, this is when a liquid becomes a solid, and that's certainly not happening when you put hand sanitizer on a patient's skin. It does not become a solid, so it's not freezing. Option B, condensation, is when a gas turns to a liquid, and we're not offering an alcohol-based hand sanitizer to a patient in the gas form to begin with. It's a liquid to start off with, so we can go ahead and rule out condensation. Option C, vaporization, is when that alcohol liquid, that hand sanitizer, becomes a gas. So you rub that hand sanitizer over your patient's skin or even over your own skin after you wash your hands, and you can feel that cooling sensation as that liquid becomes a gas. And then finally, option D, sublimation. That is when a solid becomes a gas or goes directly from a solid to a gas. And we are not offering hand sanitizer as a solid. So we can go ahead and rule out sublimation. All right, I got one more practice question for you guys before our review, and it's a good one, so I'm going to go ahead and include that. So the next question is, which of the following statements are true regarding the densities of solids and liquids? So keep in mind all properties of matter for solids and liquids and focus on density for these two. What is true? Go ahead and give yourself 1 minute to read through and work this out. All right, everybody, welcome back. Which of the following statements are true regarding the densities of solids and liquids? Here are the correct answers. Good job to those of you who got all three. Solids are typically have a higher density than liquids because their particles are closely, densely packed together, so you can fit more particles in the same amount of space. Liquids are less dense than solids, depending on that material. Option C, the density does change based on the state of matter, as opposed to the way option C is worded, where it says the density does not change. Density absolutely changes depending on the state. Again, solid versus a liquid. As a solid in a given amount of space, the particles are just more tightly packed together due to its nature, so you can fit more mass in that given amount of space as opposed to a liquid. So the density absolutely changes. Option D is true. That was a correct answer. In general, solids maintain that fixed shape, while liquids will always take on the shape of their container. And then option E, the density of a solid is always greater than the density of a liquid. Your key here is that word always. This is true most of the time, but not always. We're going to talk later in this webinar that, for example, ice, which is solid water, is actually less dense than its liquid version of water. And this is a unique property just to water that makes life exist. And it's a fun concept to talk about. So we'll talk about that later in this webinar when we get to water and its universal properties. But let's wrap up 3.2. Matter makes up your entire physical world. Matter has a specific mass, volume, and density. And matter exists in various states, solids, liquids, and gases. But those states depend on the amount of energy that are found in those particles. So remember, solids would have the least amount of energy, working your way towards gases, which have the most amount of energy. And these states of matter can change phases. So if we add heat, or if we take away heat, we change the phases. And those phases, remember, are evaporation, freezing, condensation, melting, sublimation, and deposition. We're going to move right into describing chemical reactions. We've got about an hour left. Remember, if I am ever moving too fast for you, this is a crash course. This is very surface level. If you need more content, or you need it at a slower pace, go ahead and check out our on-demand videos. Within our on-demand videos, you're able to access timestamps, which allows you to jump ahead to just certain areas within each one of these units to really individualize your learning path. So keep those on-demand videos in mind. I think that they are absolutely crucial for a learner to master the TEAS test. So check those out. But thanks for hanging in there with us as we go through this pretty quickly. All right, let's begin describing chemical reactions. If we're going to begin describing chemical reactions, it is essential that we start with and come back to valence electrons. Okay, so just a reminder, valence electrons are those electrons in the outermost shell or orbital of that element. Okay, valence electrons, since they're the outermost, those are the electrons that are going to come into direct contact with other valence electrons. So these are the electrons that participate in chemical reactions. And that means atoms are either going to lose electrons, gain electrons, or they could share electrons. So let's use the periodic table to remind ourselves of the patterns here, how we can determine the number of electrons, and begin to even make predictions about, will an atom lose, will it gain, will it share electrons. So I've added some numbers here since the last time we looked at this periodic table. So I'm using our groups, remember those vertical columns. So group 1, that first column here, 1, will have 1 valence electron in its outermost shell. Column 2 will have 2 valence electrons in its outermost shell. The next grouping for 3 valence electrons can be grouped as follows. So a good middle chunk of this periodic table right here will have 3 valence electrons, followed by 4, 5, 6, 7. And that final column, I think it's technically group 18 if I were to count individually all the way across. And that means that there are 8 valence electrons. So you can use that periodic table to help you understand how many valence electrons each atom will have. So let's start with if an atom will take, so gain an electron, or if it will lose an electron. Remember, we called those atoms ions. If it will take electrons or if it loses an electron, you're messing around with that overall charge, which makes that atom an ion. So if an atom loses electrons or takes on electrons, the bond it's making with the others is simply called an ionic bond, because it makes an ion. So it's one ion interacting with another ion. It's one atom taking on electrons, and it's another atom right next by that is happy to give them away. So these two together Each one is an ion, but together they make an ionic bond. So just to clarify, in an ionic bond, one atom loses electrons, one atom is happy to gain electrons. How do you know which one? Well, when you look at these atoms on the periodic table, so let's look at lithium and let's look at fluorine. I'm going to go back a slide. Lithium is in group 1. It has one valence electron. Okay, and remember, in that outermost shell, it's in row 2, so it has 2 shells around it. That outermost shell can hold 8. It can hold 8, okay? But it only has 1. So does it make more sense to just give away 1 and now I don't have that outer orbital to fill anymore? Or does it make more sense to take on 7? Well, think which one's going to require the least amount of energy. Get rid of 1, take on 7. Numerically, it just makes more sense to get rid of 1. So lithium is happy to get rid of 1 valence electron. Let's look at fluorine. Fluorine's on the other side of the periodic table. It is in group 7. So when we look at fluorine's outermost shell, they could have 8, because they're in that second row. So that outermost shell can have 8, but they only have 7. Does it make more sense energy-wise to get rid of all 7 or take on 1 more and fill that outer shell? Hopefully you're thinking it takes on 1 more. It's just less work to take on 1 versus get rid of 7. So lithium and fluorine, it's like a perfect match. Fluorine desperately wants 1 more electron. Lithium desperately wants to get rid of 1. It's perfect that they're near each other. And because of this exchange of an electron, you create a cation. Lithium got rid of 1. Okay, it'll get rid of 1 of these, and it will become more positive since you're dropping off an electron. Whereas fluorine is happy to take that extra electron on, and electrons have a negative charge, so fluorine becomes an anion. It becomes more negatively charged. These opposite charges attract to each other, allowing it to create that ionic bond. But another type of bond that can occur is not through giving or taking on electrons. Instead, you're sharing electrons. You're sharing. And I like to really reference this prefix co to help you remember sharing, because we use this prefix co like when we talk about co-parenting or co-teaching. You're doing the job with somebody else. It's a shared responsibility. So covalent, we're talking about valence electrons, and that prefix co means to do together, to share. So right here, covalent in and of itself means share electrons. So covalent bonds, covalent electrons, are going to form electron pairs. See how these orbitals overlap with each other? Because neither one of them is giving them away. They're just overlapping and saying, hey, you can share mine and I'll share yours. This is typically seen between 2 nonmetals. So a really quick way to identify if you're looking at a covalent versus an ionic bond, look at the element. Oxygen, for example, is a non-metal. So between 2 nonmetals, this is a covalent bond. Whereas lithium, going back to our periodic table, it is an alkali metal. So with an ionic bond, you're looking at a metal and a nonmetal. Covalent bonds, you're looking at a bond between 2 nonmetals. So that's just a quick way to help you distinguish or make a prediction what type of bond would be occurring. So I want you to recap that and put that into your own words. So take a minute in your notes right now, or just mentally, distinguish between covalent and ionic bonds. How would you describe each of those? Go ahead and give yourself a minute to do so. All right, let's talk about how covalent and ionic bonds are different. Let's distinguish between the two. Ionic bonds form when electrons are transferred, okay, so either gained or lost, and they create oppositely charged ions that attract towards one another, while covalent bonds involve the sharing of electrons between atoms. And I guess bonus points if you included in your explanation that ionic bonds would occur between a metal and a nonmetal, whereas covalent would occur between two nonmetals. All right, so moving into chemical equations then. Chemical reactions that we just described can occur, ionic or covalent. They can be expressed as chemical equations. That means we've got reactants and we've got products on two opposite sides of an equation. So the reactants are always going to be your starting materials. The products are always going to be the end materials. But chemical equations can be reversible, meaning that they don't just go in one direction like I've got listed here, but look at the example below. They can go in two directions. But chemical equations can still just go in one direction, and we would consider that irreversible. So let's talk about the two. In reversible reactions, the products can react to form the original reactants. So you've got like this back and forth happening. Reactants make some products. So we've got sodium and chlorine making sodium chloride. But then sodium chloride, which is salt, if you dissolve salt in water and that water evaporates, for example, those salts can recrystallize into their individual parts. In an irreversible reaction, the products cannot easily revert back into those original reactants. And you'll know that because of that equation will be represented with an arrow in one direction as opposed to two directions. But when you are looking at an equation, you'll not only see element symbols, you will also see various forms of numbers next to those symbols. So those numbers can either be subscripts or they can be coefficients. These numbers help you to visualize how much of each substance is present. And for a chemical reaction to occur, you need certain amounts of each component to carry out that chemical equation. So we have to make sure that chemical equations we are working with are balanced, that we have all parts of matter accounted for, that we're not starting with stuff that just completely disappears and never shows up in the products. Matter cannot be created or destroyed. That's a law. Matter cannot be created or destroyed. So whatever you start with in the reactant side, you use math to represent that, the same amount of stuff should still wind up in the product side. It may take on a different form, but that doesn't mean that the quantity of those individual atoms changed. So we balance equations to show and prove that concept. So let's start with subscripts. Subscripts are the smaller numbers that are going to hover down below the individual atoms. And when looking at a model here, for example, for carbon, and then there's the 4 hydrogens, that subscript 4 is after hydrogen. So that 4 is only telling you that in this entire molecule, there are 4 hydrogens. This 4 is after the hydrogen, so it doesn't apply to this carbon because it's not even next to the carbon. So a subscript is just going to refer to the atom that is immediately before it. Let's take a look at coefficients then. Coefficients or moles, which we'll talk about when we talk about solutions and solubility. Moles is just another way to quantify molecules, for example, but we can call them coefficients like we do in math. Coefficients are this big number out in front of this entire molecule. So a coefficient is telling you that there are 2 sodium chloride molecules, and I've got that shown here with a visual for you. So as opposed to a subscript, which is a number referencing an individual atom in that entire molecule, A coefficient is out in front of this entire molecule. So it is, almost think of it like the distributive property for math. This 2 can be distributed and applied to sodium, Na, and to chlorine, Cl. And that's what we see here in this model. When you balance equations, you can only change the coefficient. That's the only number you can change to balance an equation. You cannot change the subscript. Let's break this down and practice it together with a little guided practice. So we're going to start with this unbalanced equation, okay? You got 2 hydrogens reacting with 2 oxygens, and it creates how many molecules of H2O, which is water. Okay, so right now, notice step 1 says unbalanced. So let's recognize why it's unbalanced. On the reactant side, you have 2 hydrogens. On the product side, you have 2 hydrogens. That's equivalent. That's balanced right now, but not these oxygens. On the reactant side, you have 2 oxygens. On the product side, you only have 1. There's no subscript here. There's no coefficient. So all you have is 1 oxygen, 1 as opposed to 2. This is unbalanced. So we get to play around with the coefficients only to make this balanced. It's like a numerical puzzle, you guys. Balancing equations is kind of fun. So let's work it out. To help us, I've created some visuals to help you see the numbers before your eyes. So again, 2 hydrogens on this side, 2 oxygens on the reactant side. But when we look at the products, we only got 1 oxygen. So this is unbalanced. Okay, so you need to think, what can I do to these coefficients to make them balanced? Hydrogen's already balanced, so I don't really need to put a coefficient here right now. And this coefficient, or this oxygen, has 2. If I were to put a coefficient here, I'm only going to increase this amount of oxygen and make it even more unbalanced as opposed to this oxygen. So I don't want to mess with either coefficient on the reactant side. When I look at the product side, though, I only have 1 coefficient to play with. And I've got 2 hydrogens and 1 oxygen. Whatever I do to this coefficient here will affect both hydrogen and oxygen numbers, okay? So starting with just oxygen, because we know that's what's unbalanced, I've got 1 over here, and I've got 2 over here. How am I gonna make this 1 oxygen get equivalent to 2? What kind of mathematical trick can we add in front of here that can be distributed through this molecule to make 1 equal to 2? And I see some of you giving me good feedback already. You're already brainstorming and saying, hey, let's put a 2 in front of that water. And you would be correct. So I've updated the next step. I've added 2 for that coefficient in front of that water molecule. So not only do I have 1 water molecule now, I have 2. That's what that 2 coefficient is representing. Okay, so I've added 1 coefficient. Let's recount what we have. Let's take inventory once more. With this 2 on the product side, I now have, so you can either use the numbers and go 2 times 2, or you can use the model here and count. I've got 1, 2, 3, 4. 4 hydrogens in my picture, and 2 times 2 equals 4. Okay, so 4 hydrogens here. And 2 times 1 oxygen gives me 2 oxygens. So 4 and 2. Let's go back to our reactant side. I've got 2 oxygens. So now my oxygens are balanced. Excellent job. Our oxygens are balanced. 2 on the reactants, 2 on the products. But my reactant hydrogens, there's only 2, as opposed to the product side, which is 4. So I need to make that hydrogen equal, balanced to the hydrogens on the product side. I've got 4 on the product side. I'm at 2. How can I make 2 become 4? What number do I need to place in this coefficient to make that hydrogen balanced? And I'm seeing some good feedback so far. Again, you guys are telling me to put another 2 up there, so I will, because you are correct. So now I've got 2 times 2 hydrogens on the reactant side is 4 total hydrogens. Let's count that on the product side. 2 coefficient for my water, 2 times 2 is 4 hydrogens. Those are equivalent, those are balanced. Let's look at oxygens. I've got 2 oxygens on the reactant side, and I've got 2 oxygens on the product side. This equation is now balanced. So notice as we did this work, you take inventory of what you have, you play with the coefficients and multiplication to figure out how to balance one atom at a time. And after you alter a coefficient, always go back and take inventory of each atom again. That will give you direction on what the next atom is that needs to be manipulated. And just keep working the puzzle back and forth until they are balanced. All right, let's do a couple of practice questions before we recap. This practice question says, which of the following are covalent bonds? Select all that apply. Give yourself 1 minute to do this one. All right, everybody, that minute sure does go by fast every single time. Hopefully with this question, you were able to quickly use the trick. If it's a nonmetal and a nonmetal bonding, or if it's a metal and a nonmetal bonding. That should help you quickly identify covalent bonds. The covalent bonds out of these 4 options are option B and option D. We can rule out A because A, you instantly see sodium. Sodium is a metal. That's a metal and a non-metal. That's an ionic bond. Option B is carbon and oxygen, both nonmetals, covalent bond. Magnesium is another metal, so we can rule out option C. And option D with hydrogen and nitrogen, 2 nonmetals, that's going to be a covalent bond. Good job to those of you who did options B and D. All right, this next one is asking you which of the following equations is balanced. So just take inventory, reactants versus product side, count up both sides. Which equations are which equations is balanced? All right, guys. You guys, I am so very proud of you. For those of you who are sharing your responses with me, I'm saying nothing but the correct answer for the following question. Which of the following equations is balanced? There's only one, and it's option B. So great job to everybody who quickly did your ratios and figured that out. So option B, both sides have equal atoms. There's 2 nitrogens on both sides. And when it comes to the hydrogens, there's actually 6 on both sides. Remember, you take that coefficient times the subscript. 3 times 2 is 6. 2 times 3 on this side is 6. So B is balanced. When it comes to option A, oxygens are unbalanced. We did this one as guided practice. Hopefully you noticed that and you instantly were like, hey, we did this, it's not balanced. Check that one off the list. Option C is unbalanced. The oxygens, again, are not balanced. You've got 2 over here in the reactant side, and you've got 6 just within this carbon dioxide molecule here, and then another 4 in this water. So definitely not balanced here. And then option D, aluminum and oxygen both are unbalanced. You've got 1 versus 2, and you've got 2 versus 3. All right, let's recap. Valence electrons are the electrons in the outermost shell, and they're responsible for chemical bonds. Ionic bonds versus covalent bonds. You can distinguish based off of periodic trends on the periodic table. So ionic bonds are going to rely on electrons being transferred. It will result in anions and cations. Whereas covalent bonds, you share electrons, and that's typically between 2 nonmetals. When you read chemical equations, you need to make sure you can distinguish between the subscripts and coefficients. Coefficients are the only thing you can manipulate when balancing a chemical equation. But when you are balancing a chemical equation, remember, you're really accounting for all parts of matter. Matter cannot be created or destroyed. So that means all parts that you start with in your reactants should equal all parts you end up with in your products. And you're proving that law by using math to account for all parts of matter. Okay, we're going to move into conditions that affect chemical reactions, because now that we understand that these reactants become products and sometimes it can go in reverse and all matter is accounted for, what are some conditions then that affect a chemical reaction? Does it speed it up? Does it slow it down? How can it be changed? So chemical reactions are processes where substances known as reactants will change into their new substances that we call products. So just remember, they can be reversible. Chemical reactions can be reversible. And when we talk about a chemical reaction, sometimes chemical reactions will reach this state of what we call equilibrium. And you hear the word equal in equilibrium. So equilibrium is when a chemical reaction reaches a point where the amounts of those starting materials, those reactants, balance the products. This reversible reaction, it stays constant. And that ratio isn't really changing anymore. They're just equivalent, and they're in this like state of equality. So in the human body, actually, many chemical reactions strive. They like really work hard to achieve equilibrium, especially reactions that are involved in your metabolism. But in reality, the human body will often prevent these equilibrium reactions from like really achieving equilibrium to keep that chemical reaction moving in the direction needed to keep that body surviving, because your body is constantly changing its demands and its needs as it interacts not only internally but with this environment around itself. So these are the factors that will influence reaction rates: concentration, pressure, temperature, and catalyst. Excuse me. Understanding these factors that influence reaction rates are important for you as a future nurse. For example, many medications rely on specific reactions within the body in order to be effective. So nurses need to understand how factors like temperature and concentration can impact the body's ability to absorb and metabolize these medications in order to make sure these medications are effective. So let's break down each factor. The first one we'll talk about is concentration. Concentration refers to the amount of a substance given in volume. So how many particles are in this given amount of space? Okay, we know volume, we've talked about density. How concentrated is that solution? When there are more particles in a given amount of space, that's just more opportunity for these particles to collide, which increases the reaction rate. If there are more reactants, they're more likely to collide with each other, creating more products. So increasing the concentration increases the reaction rate. It speeds it up. And then on the flip side is also true then, right? If you really dilute a concentration, so you would add more water to something and then you spread those particles that are in that water farther apart, they're not as likely to collide with each other. So you would slow down the reaction rate. Pressure refers to the force exerted on a surface by the continuous collision of gas molecules. So if we have really high pressure, let's take that scenario, increasing the pressure of gas reactants increases the concentration of that gas. So if we increase the pressure, we follow this model and follow the arrows, we push down, we're increasing the pressure. Notice how in this picture to the after picture, you're actually reducing the amount of volume by increasing pressure. That's a gas law. So if we play with volume and reduce volume, you increase the pressure, which means that you're giving these particles more energy, but also less room, increasing their ability to collide with each other. And that increases the reaction rate. But then again, the opposite is true too. So alleviate this pressure, right? Remove these arrows. This volume expands because that pressure has come off. So you're opening up that space. Well, since there's more space, going back to the before picture, when there's more space, these particles aren't as densely packed. They're spread apart. Well, at least they're spread apart more than when they were before. That means these particles won't react or collide as quickly. So lowering the pressure would slow down a chemical reaction. Temperature affects reaction rates by increasing the kinetic energy of your molecules. So if you add heat or temperature, you excite the particles. When you excite particles, the particles just move around like crazy. When they move around like crazy, they're more likely to collide with each other, increasing the reaction rate. As opposed to cooling down. As you cool down a substance, you are allowing energy to escape. And since there's not as much energy, those particles aren't as excited, they don't move around as much, therefore they're not as colliding, or they're not colliding as frequently. And so you slow down your chemical reaction. And our final factor here are catalysts. A catalyst is a substance that speeds up a chemical reaction, because it reduces the amount of energy that's needed for that chemical reaction to even start. But the thing is, a catalyst is not being consumed or permanently changed in that chemical reaction. It's simply present. And its presence alone reduces the amount of energy for these two other reactants to react with each other. So it speeds up the overall chemical reaction. So one more time, a catalyst will reduce the amount of energy needed for a chemical reaction to start. We call that activation energy. It just reduces the amount to get started. But it's never consumed in the process. Some typical catalysts are enzymes, like proteins in your body that speed up biochemical reactions. For example, you've got amylase. This catalyzes the breakdown of starches into sugars in your digestive system. So that's just one specific type of a catalyst that will cause a chemical reaction in the body. It causes it to become faster, it speeds it up, but amylase itself is not being used as starch turns into sugar. It's just simply present. Okay, let's check in on your learning. Which of the following influence the rate of chemical reactions? Select all that apply. Is it temperature, concentration, catalyst, pressure, or water? Select all factors that apply. If you chose options A, B, C, and D, you are correct. Those are the four factors that we broke down and discussed. So remember, when you add or manipulate temperature, you absolutely change a chemical reactions rate. By adding heat, you increase a chemical reaction. If you decrease heat, you're slowing down a chemical reaction. When it comes to concentration, if you add more particles, they're more likely to collide, so you increase a chemical reaction. Whereas if you take away particles, you make it less concentrated, then it would reduce the chemical reaction rate. A catalyst will always speed up a chemical reaction simply because of its presence. It will speed up because it just reduces the amount of energy that these two reactants need to get started. Pressure, as you increase pressure, you reduce volume, so you make and force these particles to come into contact with each other more often, increasing a chemical reaction rate. And water itself has no direct impact on a chemical reaction. In fact, you will find most reactants are dissolved in water. The presence of water alone does not speed up or slow down a chemical reaction directly. And our next question is, how does a catalyst affect a chemical reaction? So think about what we said for a catalyst. It affects a chemical reaction in a very specific way. Which way is that? You got 1 minute to think of your answer. All right, a catalyst affects a chemical reaction by speeding up the reaction. So I see in our responses, everybody understands that portion very clear. Great job. A catalyst will speed up the chemical reaction, but it does so by reducing the amount of energy that's needed to get started. And I did reference and say that we do call that activation energy, but it reduces, it decreases the amount of energy. So if it doesn't need to reach or obtain as much energy to get started, it happens quicker. As opposed to option D, if we increased the activation energy, we're just waiting around even longer for that chemical reaction to occur because we're waiting for those reactants to get more energy to even start. That would slow down the overall reaction. All right, Le Chatelier's principle is a fundamental concept in chemistry because it says that if a system is at equilibrium, and it is disturbed. Okay, so going back to our concept about a chemical equation in equilibrium, and we said that actually our body's always kind of trying to achieve equilibrium, but it's always responding to constant changes. So here's where Le Chatelier's principle comes in. If your system is at equilibrium and it's disturbed, your system will shift in a direction that counteracts that disturbance in order to get back to equilibrium. So it's just this back and forth play of responding to those factors we talked about. Let's say that you are exposed to, like a really big shift in temperature. So I'm from the Midwest, and last week we had days that neared 60 degrees, and tomorrow we're looking at freezing temperatures and freezing drizzle. That's just the Midwest for you. So when your body shifts, from one type of environment to another, and a pretty extreme environment to another, there's internal mechanisms and measures and chemical reactions that will always try to maintain that balance. So luckily for us, being humans, we always maintain that internal balance, as opposed to other life forms, like lizards, for example, that are just at the mercy of whatever temperature that their surroundings are. We have the ability to maintain balance and equilibrium within due to chemistry. So Le Chatelier's principle is just referencing those changes, that if temperature changes, pressure changes in your body, concentration changes, your body is going to fight to counteract that upset and try to get back to balance. We've got these reactants that are balanced with with the products. We've got that irreversible situation happening until equilibrium is reached. Let's review this section then. Chemical reactions include reactants and products. And chemical equilibrium is when the forward reaction rate equals the reverse reaction rate. Some chemical equations have both that forward and backward reaction. Some chemical equations are only a forward reaction. There are factors that influence chemical reaction rates, of course, and those are concentration, pressure, temperature, and catalysts. And whenever you alter those conditions, whenever you play around with concentrations and pressure, temperature, and catalysts, always remember Le Chatelier's principle that the body is always working to achieve equilibrium, to balance those disturbances. All right, we're moving into our last two sections, and we've got just about it looks like 23 minutes remaining on my clock. So I think we're doing pretty decent on time. I'll do my best to get you guys done by 8 o'clock tonight. If you're still with us, thank you. And remember, if you need more, if you need any of these ideas in greater detail at a slower pace, you want more practice questions, and I hope you want all of those to help you be your best self, to prepare for not just, one TEAS test, but also just to really develop a good foundation of chemistry learning or science learning or English learning, math, writing, reading. Check us out on Archer Review for all things that we have to offer you guys. Let's move into properties of solutions. Solutions are a type of mixture where two or more substances are evenly mixed together. And a solution is made up of two major components then. You've got the solvent, which is the substance that does the dissolving. Oftentimes you can identify the solvent because it's the greater concentration of the two. There's more solvent than there is solute, typically. But then solute is the substance that gets dissolved into the solvent, oftentimes present in smaller amounts than the solvent. So one more time, when you're looking at solutions, a solution is always going to be made up of a solvent and a solute. The solute is what gets dissolved in the solvent. And when we look at solutions, we can describe those solutions by talking about their solubility. How well does that solute dissolve in other substances? Okay, and you got to remember this phrase, like dissolves like. Okay, that will help you remember different properties about solubility, or how soluble is something in this other substance. So our first two terms that we see here are hydrophilic and hydrophobic, the top two in this table. And my little pictures here hopefully help you remember the difference. So we go at the prefix hydro for both. Hydro refers to water. And the second part of this word is either philic, meaning liking, loving, hence the heart, or phobic, phobia, a fear of, hence the broken heart. So if something is, if a solute is hydrophilic, it loves water. It will dissolve well in water. It loves it. But if the solute is hydrophobic, this means it is water fearing, does not dissolve well in water. So how do you know the difference? How do you know if it's going to love water or if it's going to hate and fear water? There's another component to these solutes that you have to look back to, and it has to do with the electrons and the charges that we talked about. So if a substance has electrons that are unequally shared, okay, so let's look at this little picture down below here of, I've got two hydrogens and a big oxygen. This is a water molecule right here. See how I've got on this molecule some pluses on this end by the hydrogens, because we talked about hydrogens are more than happy to give away their electrons. So they have these overall positive charges. Well, in that same water molecule, you've got the oxygen atom. And oxygen is kind of the opposite story, right? It's on the other end of the periodic table. It wants more electrons, so its charge is overall negative. So just in one molecule, you've got this unequal distribution of charge. On one end of this molecule are more positives, the other end of this molecule is more negative. Could be water, could be any other molecule that has that similar nature. If electrons are unequally shared or distributed across this entire model, leading to part of the molecule that's positive on one end and the same molecule, but it's negative on this end, we call that polar, a polar substance. Okay, a polar substance. I think of poles like the North and the South Pole. They're just opposite ends. So on opposite ends of the molecule, I've got two opposite charges. So polar molecules, like water, which is also a polar molecule, they're gonna love and dissolve well in water. Here's where that phrase, like dissolves like, comes in. Since water is polar, other substances that are also polar are going to love water simply because the positive pieces of one end of a molecule are going to attract the negative end of a water molecule. They're going to dissolve well. But some solutes don't like water because they're non-polar. So what does that mean? Well, if polar is unequally sharing electrons, the non-polar is the opposite. Electrons are equally shared. Take a look at our two oxygens. Remember, with a covalent bond, there is really no swapping of electrons. Instead, they share them. And so electrons are equally shared. There isn't a part of this entire molecule that's more positive or more negative. They're just distributed equally. And because of the no slight charge, there's really no part of this molecule that's going to attract well to one part of this water molecule. They just don't jive because of that electron distribution. And these nonpolar substances then are hydrophobic. They're not going to dissolve well in water because water's polar and some substances are nonpolar, like fats, butter, oils, for example. So water is polar, like I said, due to that molecular structure. Its electronegativity, so oxygen having a strong affinity for electrons, hydrogen having a lesser affinity for electrons. And because of that, you have an uneven distribution of charge. So this is just a recap of what I verbally said on the previous slide, just to make sure you get this all into your notes in case you missed something. But what's interesting, guys, is all of these properties of water, the polarity of water, allows water to be just really unique. And water is truly, because of its uniqueness, because of its polarity, allows for life to exist. You and me do not exist without water and its property for being polarity. That is huge. So let's break it down simply to understand it, and to appreciate it, appreciate that chemistry gives rise to life. So, hydrogen bonds, you see here, hydrogen bonding is occurring between this hydrogen here and this dashed line connecting to the neighboring water molecule with oxygen. This dashed line it's referencing the fact that it's not a true but like more like an attraction. So this positive charge on the hydrogens is just naturally attracted to that negative charge of a neighboring water molecule. This positive attracted to a negative. That's the nature of a hydrogen bond. And it's not always just between a hydrogen and an oxygen. It's going to be between the hydrogen and any other kind of electronegative atom. But due to this hydrogen bond here, okay, this affinity, this attraction between opposite charges within these water molecules, that's what allows water to have these four essential criteria: a high specific heat, its ability to be cohesive, to be adhesive, and to have surface tension. Okay, so let's talk about each one of these. The high specific heat factor. So the hydrogen bonds allow water to absorb and retain heat really, really well, stabilizing temperatures in environments and organisms. This property helps regulate climate and maintain stable internal temperatures inside of your body. So you can thank hydrogen bonds for the fact that, your body temperature remains relatively stable, even though you can walk out into, a blizzard or walk out into the desert. You're going to internally maintain a temperature due to those hydrogen bonds. Water has the ability to be cohesive. So cohesive means that water molecules are just attracted to each other. They will stick to each other. Whereas adhesion means that these water molecules are able to stick to something else. So like water droplets sticking onto a glass window, for example. Not only does it have the ability to stick to itself, cohesion, but it has the ability to stick to other surfaces as well, and that's adhesion. And this is what allows for vital processes like the transportation of water in plants, for example. Plants are able to take water from the roots down below all the way up through its stems and eventually to the leaves due to the capillary action occurring within the water molecules and its ability to stick to the other surfaces on its way up. And these cohesive forces create surface tension. So water's ability to stick to itself creates surface tension, allowing for, like small organisms to walk on water, for example. It really influences water's interaction with other surfaces. Now, water is the only unique substance where the molecules become less dense as it becomes a solid than as opposed to when it is a liquid. So this unique property allows for, water becoming solid is ice, right? And if ice is less dense than its liquid state, water, this is what allows for, like ponds and lakes, for ice to float to the top of that body of water, which then allows for life to continue to exist down below. If this unique property of water wasn't occurring, then our ponds and our lakes would freeze entirely from the bottom all the way to the top. Everything in that environment, in those ecosystems, would die because it can't survive when it's all frozen for a good solid period of time. So what a unique property that truly allows for life to exist. And then finally, Water is known as a universal solvent because water has this ability to dissolve a wide range of substances due to its polar nature, of course, from hydrogen bonding. It makes it an excellent universal solvent. All right, but when it comes to solutions, you can mess around with how concentrated or diluted those solutions are. So concentration tells us how much of a substance, like the solute, is in that solution. And dilution is then the opposite. It means adding more of your solvent, your liquid, maybe water, the universal solvent, to make that solute less concentrated. And you will come across many different types of units to express concentration, but I've just given you a brief list of some of the most common. So ways to express concentration, you could say how many grams per milliliter. So grams is referring to a solid, milliliter is volume, a liquid. So how much of your solute do you have in the total amount of volume of your solvent? Another unit you would see is how many moles per liter, and you can even see concentration expressed by percent volume. If you want practice questions on these different types of concentrations, don't forget to check out our on-demand videos. Depending on the type of solution, if it's concentrated or if it's diluted, we've got words to describe to help you as a learner recognize, is it more diluted? Is it really concentrated? So one type of solution we would call unsaturated. An unsaturated solution has less solute dissolved than the maximum amount it possibly could. You can add more solute to this solution. It could take more on. That's what unsaturated means. A saturated solution has the maximum amount of solute that could be dissolved at that certain temperature for that solution. It's maxed out. And then you can also have a super saturated solution, which means that there is more solute that is dissolved than usual due to that higher temperature. Now, solutions are transported in various ways throughout your body in order to maintain equilibrium or homeostasis and, to provide the reactants necessary for different chemical reactions. And there are two types of transport we're going to talk about next. This first one is passive transport. Passive transport is the movement of substances without using energy. It's not using energy because passive transport takes advantage of this concentration gradient idea. So when we look at the two ways that things can move around in your body without using any energy, it's through diffusion and osmosis. And there's a slight difference between the two. So diffusion is the movement of molecules from a high concentration into an area of low concentration. Here is that concentration gradient I was referencing. If molecules are moving from an area where they're highly concentrated into an area where there's fewer of those same particles, that's diffusion. It takes no energy to move those particles into an area where there's not as many in order to balance this out. Osmosis is the movement of water specifically from a high concentration to a low concentration. And it does require the movement across a membrane in order to make that happen. But osmosis aims to equalize it's using the movement of water, but osmosis is really trying to equalize the solute concentration on either side of that membrane through the movement of water. Active transport then, as opposed to passive transport, active transport does use energy. And it uses energy because it's going the opposite direction now. These are the movement of molecules going from low concentration to areas that are already packed full of particles. So to add even more to that high concentration area, it takes energy to do that. This is going against the concentration gradient. So passive transport, no energy because it goes with the concentration gradient. It goes from high to low. Active transport uses energy because it goes from low to high, it's going against the concentration gradient. Let's do a couple practice questions before we recap. So sugar, salt, alcohol, and oxygen are all what kind of substances that are attracted to water molecules and dissolve well in water? Give yourself 1 minute to answer this question. Option A is your correct answer for this question. Good job to everybody who shared their thoughts. Sugar, salt, alcohol, and oxygen are all hydrophilic substances that are attracted to water molecules and dissolve in water. Hopefully that second part of that question is what led you to choose hydrophilic. These are substances that are attracted to water. Remember, that means hydro, water, and philic means like. It likes water. It will dissolve well in water. Option B, nonpolar, is incorrect because if it's dissolving in water, then these would have to be polar substances. Nonpolar substances do not dissolve well in water because water is polar. Remember, like dissolves like. Option C, hydrophobic, is incorrect because phobic means dislike. Phobic is phobia, it's afraid of. It will not dissolve well in water. And then option D, insoluble, means that they don't dissolve. But the question says that they do, so this option is quickly ruled out. We'll do one more practice question before we recap, just so I honor your guys' time. This question is distinguish between passive and active transportation. So give yourself 1 minute to summarize the differences. All right, let's summarize the differences between passive and active transportation. I'll click this next slide for you. It kind of looks like a lot of words, but we'll just summarize it. Remember, passive transport means that it's movement of particles without using any energy. It takes advantage of the concentration gradient, so it will move particles from an area of high concentration into an area of low concentration. Whereas an active transport requires energy because it is moving against the concentration gradient. Particles then are moving from areas of low concentration into an area of high concentration. And let's recap section 3.5. Solutions are made up of two parts, a solvent and a solute. Remember, a solvent is going to be in greater quantity than the solute, so that helps you distinguish between the two. Solubility describes how well a solute dissolves in that solvent, and that all depends on if it's hydrophobic or hydrophilic. Does it hate water? Does it love water? Is it polar or is it nonpolar? How is that distribution of charge across that molecule? Is it uneven or is it even? Remember, water is polar, so anything else that is also polar is going to dissolve well. It's going to be hydrophilic. Types of solutions are unsaturated, saturated, and supersaturated. And concentration is simply how many particles are in a solution. And you can dilute a solution. You can add more of the solvent and make it less concentrated. Water is a universal solvent, and it is also polar. And these properties of water are unique to water, and it allows for life to exist. And then there are transportation of all of these molecules, all of these solutions that we're describing. We need to transport them in throughout our body. And there are two ways to do so, through passive transportation and active transportation. All right, we are in our last section of our chemistry webinar tonight, and it is exactly 8 o'clock right now. If you cannot stay with us, for 10 more minutes, absolutely fine. Just don't forget to take that survey, please, and also to check out our other options that we have for you at Archer Review. You can have access to those QR codes from the beginning of these notes. That's in our chat rooms if you are leaving us. Otherwise, I'm going to promise we're going to get this last section done in under 10 minutes. So if you've got 10 more minutes, please stick around and hang with us. I promise it'll be worth your time. Let's go ahead and wrap up with acids and bases. Acids and bases are identified using a metric that we call pH. pH stands for potential of hydrogen. So again, that measures how acidic or how basic a solution is. And we use the scale from 0 to 14. So anything that has a pH less than 7, take a look at this red extreme area going up to 7. Okay, so anything less than 7 is going to be considered acidic. Anything at 7, green here, is neutral, like pure water. That's a neutral pH. It's neither acidic and it's neither basic. So basic, it has a pH of anything greater than 7. So acids, as we said, has a pH of less than 7. But what makes it an acid? It's an acid because when this solution is released into, a solvent, these acids will release hydrogen ions. So whatever solute or kind of solution you're working with, if it releases or dissociates and releases these hydrogen ions when dissolved in water, then it is considered an acid. Okay, so an example of this could be hydrochloric acid, HCl, or looking back at your guys' pH table here. Sorry, words lost me for a moment. Looking at your pH table, lemon juice or vinegar, really common acidic household items. If you were to put that solute into water, it would naturally produce hydrogen ions. The more hydrogen ions you have, the stronger the acid it is. Bases are the opposite. Bases have a pH of greater than 7. When these solutes or substances are dissolved in water, it releases hydroxide ions, OH negative, as opposed to acids, which are H positive. So completely opposite ends of the spectrum. And some examples of classic bases are baking soda, bleach, and bicarbonates. Now, acid-base reactions typically will form salt and water when they are mixed together, and this we would call a neutralization reaction. So when you have equal parts of an acid and base that are being used, your system becomes neutral. It will have a pH in the end of 7. It's almost as if they cancel each other out, so to speak. So we've got hydrochloric acid as an example, reacting with sodium hydroxide, so a strong acid mixing with a strong base, that will create sodium chloride, a salt, and water with an overall pH of your product as neutral. So it creates a neutral reaction from a strong base and a strong acid. For example, or a typical example in your body is like your blood pH being regulated through buffer systems. So these involve neutralization reactions, ensuring proper functions of your blood. So some common buffers that you may come across as a nurse. Nurses will often administer like sodium bicarbonate to regulate that blood pH that we talked about on the previous slide. So what is a buffer? If you're going to oftentimes be offering sodium bicarbonate to a patient to regulate their blood pH, what is a buffer? A buffer will stabilize pHs, so it resists any changes in pH. This will consist of a weak acid and its conjugate base, or a weak base and its conjugate acid. So when an acid is added, the conjugate base in your buffer will react with all of those extra hydronium ions coming from this acid to reduce the overall impact on your pH, stabilizing, regulating the blood in your patient, for example. On the flip side, when a base is added to that system, you have a weak acid in that buffer that will donate its hydronium ions to neutralize that base. So we're just regulating the blood pH, a typical way to interact with buffers as a future nurse. So here's a quick practice question. Which of the following are true about acidic solutions? Select all that apply. You've got 1 minute to answer this one. All right, if you chose the following that are true about acidic solutions as options A, B, and D, then you are correct. So, option C, the one that is incorrect. So let's talk about that one for a minute. First, again, we haven't talked at all about blue litmus paper. So hopefully you're like, what is this about? And you ruled that one out. But just so you do know, litmus paper can be used to test the pH of a solution. If it turns blue, that means it's a base. If it turns red, that means it's an acid. Option E is also incorrect. Bases will release OH ions when dissolved in water, whereas your acids are going to release hydroxide, the hydrogen ions, when dissolved in water. And then option F, they feel slippery. Actually, bases tend to feel slippery, while acids do not. So good job to those who chose options A, B, and D. Let's go ahead and wrap up our last section. Acids and bases are measured using pH, which is a 0 to 14 scale. Anything greater than 7 is basic. Anything right at 7 is neutral. Anything less than 7 is considered acidic. Acids are proton donors. Remember, if it dissolves in water and it releases hydronium ions, it's an acid. Bases are proton acceptors. They release hydroxide ions, okay, when put into that universal solvent, but they will accept that proton. Neutralization reactions do occur, and it creates salt and water typically in the end. So it's an acid mixing with a base to create salt and water. They are very important in the body because these reaction types neutralize solutions in your body. But buffers also help to regulate neutralization. So buffers are present to help regulate pH in different reactions, and we talk specifically about the blood, for example. All right, guys, we did it. We were only 9 minutes, not even 10 minutes over. Let me give you some more information about Archer Review here as we wrap up. So here is that webinar feedback survey. Please scan this QR code. Give us your feedback. What are we doing well for you as a learner? What would you like to see be done differently for you as a learner? And also keep in mind, these are free webinars that just skim the surface on these concepts. So here on this page, lots more QR codes for you all. Here is where you will find all the good things that we have to offer at Archer Review beyond our free webinars. So if you want to access any other free webinars that are coming up, please scan that QR code and truly take a look, because we are amping up our webinar frequency. We're going to offer more webinars for you guys. And we're also going to be changing our style a little bit for our webinars. So instead of like a 2-hour teaching and practice question in one, we're actually going to switch up our format and try out a 1-hour teaching session followed up with either maybe that day or the next day or the next couple of days, a 1-hour, let's just go through all practice questions that are affiliated with that lesson you attended. So if that sounds like a different style of learning that would be really helpful for you, please scan that QR code, get signed up for those, try our new system out. I think it's going to be really beneficial for all learners, especially just having more access to us with these free webinars. It can only benefit you in the long run. If you missed any webinars, or you want to rewatch tonight's webinar, scan the second QR code for rewatch. Okay, so this is not just for the chemistry. This is giving you access to all of our webinars, whether it's in math, reading, English, or science. You'll have access to all of our previous webinars. Our question bank, we have completely been overhauling, like I said in the beginning, and you do have a free trial period to look into that, but of course that free trial period will run out, and there are so many questions in there, and we're only adding more every single day. So you will want to take a look at signing up for some of our packages that we offer so you have long-term access to our question bank. Next up, our on-demand videos. Our on-demand videos go into each one of our topics we cover in our webinars, but on a much greater detail. And you can pause it, you can slow it down, you can speed it up, so you can go at your own pace. But the really wonderful thing, our on-demand videos have timestamps. So let's say there's a section in that topic and you're like, hey, you know what? I know physical properties. I know about states of matter. I know acids and bases. What I really need is balancing chemical equations. We've got timestamps where you can just jump right ahead to those specific sections, get practice questions built in with it, really cater your needs as a learner. We also offer tutoring. So I'm going to show you the next slide for tutoring. Our 3 tutors. Oh, I don't know why you're not able to see the 3 pictures here. Okay, that's weird. On my end, I can see all 3 of our tutors with our QR codes. I'll just go back to this general one and talk about each one. This QR code should lead you to the web page where you can see the 3 different people. But Tammy is with English and Reading. Shelly is our tutor for science, and Brandon is our math genius who is our tutor for math. So scan that QR code to be able to access any one of those people to support you in your one-on-one needs or even in a small group. And then finally, the packages that we now have available. So if like 2 or 3 of these things here sound really good to you and you want to save some money, take a look at either our Sure Pass option or our Sure Pass Pro option. If you purchase a Sure Pass bundle, you are getting access to our Q Bank and our on-demand video. So you don't have to worry about your free trial running out. And like I said, we're adding more really awesome questions every single day. So if your free trial runs out, we're still adding more goodies in there and you're missing out. So the Sure Pass is going to make sure that you have that unlimited access to our QBank and on-demand videos. But then if at ever throughout your learning journey, you're like, you know what, I think I really need a tutor for this section, instead of paying for that separately, which you can do, but instead of paying for that separately, tutoring can be bundled into this Sure Pass Pro package. There you will be saving money as opposed to just doing the Sure Pass and then finding out later on, actually, you know what, I really do need a tutor. You can do that. It's just you're going to spend a little bit more money. So I know when you're going through school, I've been there, you're all about saving every dollar that you possibly can. So the Sure Pass Pro option just allows you to have all of those opportunities while saving a little bit of money in the long run. So thank you guys. I'll pop the survey up here again one more time for you. Thanks for hanging out with me for 2 hours of your evening. I hope it was everything you needed for just a quick crash course, refresh your memory or your knowledge on some chemistry concepts. So I'll linger here for a couple more minutes and just take care of some questions in the chat. But I hope you guys all have a really great evening, and your new year and your new semesters have all started off really, really strongly. Thanks for being here, everybody.